This is the 10th and penultimate video in the EDEXCEL C3 revision tutorial series. In the previous video, C3.9, we had an introduction to organic chemistry including the homologous series and functional groups. Today we'll be looking at two different homologous series. We will be looking at alcohol, focusing on ethanol, as well as carboxylic acids, where we will focus on ethanoic acid. Here we have a selection of uses of ethanol. So we have ethanol being present in mouthwash, in alcoholic drinks, as a biofuel, used in perfumes, and finally for disinfectant. So in this video tutorial we will look over the first three alcohols and carboxylic acids. This will be a recap from the previous video. We will look at how ethanoic acid can be formed from ethanol via oxidization. We will look at the uses of ethanoic acid as well as its reactions with metals, indicators and bases. And finally, we will evaluate the production methods of ethanol. In the previous lesson, we looked at the fact that alcohols have the functional group of OH, whereas carboxylic acids have the functional group of COOH. We also looked at how to count in chemistry, with 1 being meth, 2 being eth, 3 being prop, and 4 being bute, giving us methanol, ethanol, butanol, and propanol for the alcohols, and methanoic acid, ethanoic acid, propanoic acid, and butanoic acid as our first 4 carboxylic acids. The alcohol we're going to focus on for this video is ethanol. So you probably remember from B1 and C1 that ethanol is a clean burning energy source that produces little to no greenhouse gas. And we can see here a car from a few years ago made by Ford that ran on 85% ethanol. 85% ethanol, 15% petrol. So it would be a much lower carbon emission car. What we're interested in is how is it made? Well, ethanol can be made in two ways. The first is it can be produced from ethene. So ethene is an alkene, so we can produce that via the fractional distillation of crude oil and involving cracking using a catalyst. To produce ethanol, we react the ethene with steam at very, very high temperatures. This results in ethanol. So the ethene is produced by cracking oil, and then we can use steam in order to form our ethanol. We'll look at this in a little bit more detail in a moment. Our second way, which you probably remember from B3 as well as B1, is that we can carry out fermentation. So the fermentation of sugar from standard crops like sugarcane and corn under warm and anaerobic conditions, we can form our ethanol. So sugar goes to ethanol and carbon dioxide, and it's using yeast as an enzyme. So we've got a fossil fuel way and a renewable way. We will now look at each of these in a bit more detail. So our first method is making ethanol from ethene. This is the fossil fuel way. So as we said previously, we first need to get our ethene. Ethene can be obtained via the fractional distillation of crude oil, as well as the cracking of much larger hydrocarbons. When we add our ethene to water, this is water in the gaseous form, we form ethanol. So ethene goes in, we have our vessel with a very, very high temperature and pressure, the pressure to force the reaction to the right, and the temperature to speed up the reaction as well, and we form our ethanol. The good thing about this reaction is that any of the unused ethene can simply be put back into the vessel in order to react with steam once more. We have our symbol equation here. So C2H4, which is ethene, plus water H2O goes to ethanol, C2H5OH. We will look at this in terms of the structures of these molecules. The reaction that we are carrying out is an addition of water. It's a hydration reaction. We are adding our water to our ethene here in the presence of a catalyst to form our ethanol. So we've got our double bond in our ethene, and then we've got our ethanol here. The catalyst that we use is phosphoric acid. We can also carry out this reaction in reverse in terms of our dehydration of ethanol. So here we can see we've got our ethanol, we're forming our ethene and our water. This hydration of ethene uses very high temperatures and high pressure. It is a continuous process, so it runs all of the time. It uses non-renewable resources, so it is not as sustainable. It does, however, produce a very, very high purity of ethanol, as no byproducts are made, as well as a very high percentage yield. We end up with about 95% pure ethanol. We also have 100% atom economy, which means that all the atoms in the reactants have been converted into the desired product. Our second method of making ethanol is from organic matter. This is the renewable way. As you should remember from B1, when we looked at fermentation, as well as B3, we can make ethanol from organic matter. So glucose from plant matter is converted into ethanol and carbon dioxide by fermentation. This is carried out by yeast, who act as a natural catalyst. So we take our sugar, in this case glucose, C6H12O6, which gets converted into ethanol, 2C2H5OH in order to balance it, plus 2 carbon dioxide, 2CO2. So how does this differ from the non-renewable way? So how are the conditions required for fermentation different to those for the hydration of ethene? Well, first of all, we need to make sure we don't use too high a temperature in order to make sure we do not kill the microorganisms. So we use a warm temperature of about 37 degrees C, as well as normal pressure. Unlike the hydration of ethene, it's a batch process, so it's very much stop-start. It does, however, use renewable resources, sugar from plants. In a moment, we will look at where this sugar comes from in various drinks. However, this does mean that it is far more sustainable than the hydration of ethene approach. It does, however, produce a very low purity of ethanol, as well as a very low percentage yield, about 15%. We then need to carry out fractional distillation in order to purify this. The atom economy is roughly medium, about 51%, as not all of the reactants have been converted into the desired products. We do also get the formation of carbon dioxide. So, this then begs the question of where does the sugar come from in various drinks? So in the cases of beer, cider, wine and spirits. So for beer, the sugar comes from boiling barley in water, and in cider it comes from fermenting apple juice. Hops are then added to adjust the flavour of the beer. Beer typically has an ethanol concentration of 3 to 6%, shown as ABV on the label. Cider, however, has a slightly higher ethanol concentration of 4 to 7%. For wines, the sugars used for ethanol production come from grape juice. Different varieties of grapes produce wines with different flavours as well as different colours, with white wine, rosé wine and red wine. Wine contains a higher percentage of ethanol than beer. The question would be why? Simply, grape juice contains much higher levels of sugar than barley. Think about how sweet grapes are. This means that wine typically contains an ethanol concentration of about 11 to 14%. Spirits, on the other hand, are a type of alcoholic drink that contains above 20% ethanol. The problem with this is that fermentation will only get you a concentration of 15 to 18% tops. This is because the ethanol is poisonous to the yeast. In order to get a concentration above this, such as what we find in vodka, tequila and whiskey, which have an ethanol concentration of around 40%, the drink must go through a second process known as distillation. This produces a much higher concentration of ethanol and is very similar to the fractional distillation that you've looked at previously. In fact, it uses the same idea. In order to increase the ethanol concentration of a solution, we need to carry out a distillation. Here we have a simple setup for a distillation experiment. In the flask here we have got water and ethanol, and below it we have our Bunsen burner, which is going to be our heat source. We will heat the water and ethanol solution, and because ethanol has a lower boiling point than water, it will evaporate first. The evaporated ethanol will then travel into the condenser. The condenser has a cooling water jacket around it, so this would be attached to the tap, and then we'd have our outlet here. This causes the ethanol to condense and become a liquid. It will then drip into the beaker here. So we will end up with just our pure ethanol in the beaker here after we have separated it from the water over here. So we'll end up with water in this flask and our ethanol in this flask. We will also often put anti-bumping granules into the water and ethanol solution in order to control the boiling, in order to make sure that this doesn't boil over. It's obviously very important we do not want the water to evaporate, as we do not want it to end up in the beaker over here. By carrying out a distillation, we can increase the purity of the ethanol that is formed from fermentation. A popular exam question on the production of ethanol looks at evaluating the production methods. So evaluation questions require careful comparison of advantages and disadvantages. You must make sure you present both sides of the argument as well as a final overall conclusion. Obviously in the exam you would write this in full sentences, however it is useful to practice this by writing it out in a table. So we've got the fermentation against the hydration of ethene with advantages and disadvantages. I want you to pause the video at this point and write down the advantages and disadvantages for both the renewable and the non-renewable method. So for the hydration of ethene, the advantages are that it's a cheap process, as well as the fact that ethene is currently fairly cheap and not much of it is wasted. Remember, we are putting it back into the reaction each time. It produces a 95% ethanol solution, so it's very high purity. And finally, that it is a continuous process, so it is more efficient than a batch process. However, the disadvantages are that ethene comes from crude oil, so it's a non-renewable energy resource, as well as the fact that crude oil is running out, which means using ethene to make ethanol will become expensive as we run out of the amount of ethene that we have. Using the fermentation of glucose, the advantages are that it uses simple equipment. You do not need expensive equipment to carry this out. It is done at lower temperature, so less energy is required, and perhaps most importantly, that the raw material is renewable. The disadvantages are that the ethanol made this way is not very concentrated. It's only 10 to 20% ethanol solution, and in order to increase its strength we have to distill it, so bringing another process in. We also need to purify it after it has been produced, and it is produced only in a batch process, which is very slow and inefficient. Another argument against the fermentation of glucose is that you have to grow your raw material. If you're growing your raw material in order to produce bioethanol, you are not growing food in that area. So if you had very limited fertile land, that could pose a problem. There are also several dangers of ethanol misuse, As you should remember from EDEXCEL B1, ethanol is a depressant. This means it slows down signals in the nerves and the brains. Lots of people use alcohol in order to help them relax. However, larger amounts can lead to a lack of self-control and loss of judgment. This can lead to both social and health issues. The health issues stem from the fact that ethanol is toxic. It can cause damage to the liver and brain, as well as increasing the risk of stroke and heart disease. It can also cause weight gain, loss of memory, and death. The social issues of alcohol misuse tend to stem around antisocial behaviour, such as fighting and vandalism. People who drive or use machinery when drunk can cause massive accidents, and people who have drunk too much alcohol often suffer from hangovers the next day. This prevents them from functioning normally. This can put a strain on the relationships of the individual with friends, family, and colleagues, and can lead to problems such as domestic violence, family breakdown, and lost work. The social and health issues of ethanol misuse lead to massive strains on the National Health Service. Outside of being used in order to make alcoholic drinks, ethanol can also be used in order to make carboxylic acids. We will look at this in more detail in a moment. The other major use is in the formation of polythene and polymers used in plastic. In order to make ethene from ethanol, we carry out the dehydration reaction that we looked at earlier. This is where we take our ethanol vapour, we pass it over our catalyst, in this case a hot aluminium oxide, to form our ethene and our water. And it is the ethene that we can use to make plastics. We will now look at how we can use ethanol to make carboxylic acids in more detail. As a recap from the previous tutorial video, carboxylic acids form a homologous series with the functional group C.00H, with the double bond to one of the oxygens. The presence of this gives carboxylic acids their properties. As they are acids, they will react with carbonates, metals, and bases. We will look at these three reactions in a little bit more detail at the end of this tutorial. They are also able to dissolve in water to form weak acidic solutions. As the carboxylic acids increase in chain length, so they get more carbons, they change from a colourless liquid to a waxy solid. Their odour becomes less strong and their solubility in water decreases as well. The carboxylic acid that you need to know about is ethanoic acid. Here is its structural formula here, and its formula is CH3C00H. Ethanoic acid can be formed from ethanol when ethanol is exposed to oxygen. This often occurs in the house when a bottle of wine is left open for a few days and it will start to taste sour. This is because the ethanol has been converted to ethanoic acid. The ethanol, C2H5OH, reacts with the oxygen in the air, O2, to form our ethanoic acid, CH3C00H, and water. Ethanoic acid is better known as vinegar, hence why the wine, which previously contained ethanol, is now turned into vinegar containing ethanoic acid and so tastes sour. This means that this reaction is an oxidization reaction due to the addition of oxygen to the ethanol. Ethanoic acid is typically used to flavour food due to the tangy, sharp taste it has. That's why we use it as vinegar on chips. However, it can also be used to preserve food. This is where the food is placed in the ethanoic acid. This is known as pickling. This works because bacteria cannot survive in this acidic environment. Finally, we will now look at the reactions of carboxylic acids with various materials. Ethanoic acid and therefore carboxylic acids are relatively typical acids. This means that they will react with metals, they will react with bases and carbonates. They will also turn litmus paper and universal indicator red. They will react with metals to produce hydrogen gas. So we have magnesium and ethanoic acid, which will go to magnesium ethanoate and hydrogen. All salts made from carboxylic acids will form anoates. For example, ethanoate for ethanoic acid, whereas methanoic acid would form methanoates. The symbol equation is as follows. So we have Mg, magnesium in the solid form, plus C3CO2H in the aqueous form. We have two of these. This is our ethanoic acid. Forms in brackets CH3CO2, close brackets 2, Mg, which is our magnesium ethanoate, which is in the aqueous form, and finally our H2, our hydrogen gas. With bases, carboxylic acids will form water in a neutralization reaction. So here we have our ethanoic acid plus our sodium hydroxide, which forms sodium ethanoate and water. The balanced symbol equation is as follows. So we have our ethanoic acid, CH3CO2H, plus our sodium hydroxide, our NaOH, both of these are in the aqueous form, which forms our sodium ethanoate, CH3CO2Na, in the aqueous form, and our water, H2O, in the liquid form. Finally, for the reaction of carboxylic acids with carbonates, this again is a neutralization reaction. However, not only are we going to form water, we're also going to give off carbon dioxide gas. In this reaction, we have our ethanoic acid plus our sodium carbonate, which forms sodium ethanoate, carbon dioxide, and water. The balanced symbol equation is as follows. So we have 2 CH3CO2H, that's our ethanoic acid, plus Na2CO3, which is our sodium carbonate. The ethanoic acid is aqueous, the sodium carbonate is solid, which forms our sodium ethanoate, 2CH3CO2Na, which is aqueous, our carbon dioxide, CO2, which is gas, and finally our water, H2O, which is liquid. This concludes the penultimate video in this EDEXCEL C3 revision tutorial series, which was video C3.10, ethanol and ethanoic acid. In the final video, we will be looking at esters, fats and soaps.